So I will start this this new lecture series on Teichmüller spaces, and I will start from the beginning. I will repeat some definitions. I will give you the motivation. So this is also based on this paper of Thurston. Minimal stretch maps between surfaces, and he wrote it in 1985. I was interested in this since the beginning. In fact, that year I was spending my year in Princeton. It was just after my PhD, and then he gave me this preprint. And I was interested. I didn't. I mean, I saw it was interested. I had no idea of how I could work on this. And then I think that 5 years later, I wrote my first paper related to this work. And then I continued until now. Regularly, I think about these things. This morning, while I was preparing my lectures, I looked at all the papers which were based on this paper of Thurston. There are about 20 of them. In fact, I wrote them with co-authors, and I will tell you a little bit about this. Some of the results. In fact, looking at this paper, I had already forgotten. It's 30 years ago, but now I want to remember them and tell you about this. So this is the theme is one of the basic themes is to measure best Lipschitz constants between surfaces. And this is not. This was not new. I mean, this was not new, and I mean, I will tell you a few predecessors. In fact, for Thurston, I'm sure it was new because he used to invent everything by himself. I don't think he knew about what was done before him. So let me mention three predecessors. One of them is Lagrange. In a paper he wrote 1779. In fact, there are two papers which carry the same name, and the papers are the title of the paper is sur la construction de cartes géographiques. So I think you can read this even if it's French. The problem is you want to construct geographic maps of the sphere, which may be the Earth or even the celestial dome, and since it's a curved surface, and you want to construct a map on a piece of paper, Euclidean piece of paper, there must be some distortion. These maps cannot be distance preserving up to a scale. So Lagrange was interested in constructing maps of least distortions. In the setting of non-Euclidean geometry, in fact, like Thurston. Thurston was working non-Euclidean geometry, hyperbolic surfaces, but here we already have non-Euclidean geometry, which is the geometry of the sphere. I think one of the next time at the seminar, next time I talk, I want to talk a little bit about spherical geometry, because it's a very interesting subject. In fact, it's not as fashionable as hyperbolic geometry, but it could be it could become fashionable. And I want to tell you a little bit about some theorems of spherical geometry. So this is Lagrange. And then the next person I want to mention is Chebyshev. This is our hero. And this is in the 19th century, 1856. And he wrote 2 papers also with exactly the same name as the papers of Lagrange. And it's a kind of continuation of the work of Lagrange. I will tell you about them later. And then the third person I chose from this is from the 20th century. And this is a paper by Milner. And this is 1969. And it's about the same problem. It's called a problem of cartography. And he also looks at best Lipschitz maps between parts of the sphere, regions of the sphere, and the Euclidean plane. And you know, the problem is not easy. It's very difficult. He formulates a problem which I will talk to you about later on, and he can prove it only in a special case. Only in the special case where the region in the sphere is a disk. So you can imagine that I mean, the disk is something is the simplest region we can think of, and he can solve his problem only in that case. So okay, so now I will turn to non-Euclidean geometry, to hyperbolic geometry, and I will talk a little bit so about best Lipschitz maps. Best Lipschitz maps between hyperbolic surfaces. And this is the discovery of Thurston. You know, the problem, it turns out that this problem of best Lipschitz map is easier to deal with between hyperbolic surfaces than between Euclidean surfaces and then between spherical surfaces. And it is because of the existence of Lipschitz maps between ideal triangles, which we will talk about. And these ideal triangles exist only in Euclidean in hyperbolic geometry. So this will be the theme. So let me just say the setting. So we have S. Okay. Well, hyperbolic surface. More precisely, I have let's say a topological surface, and we want it to be well, negative Euler characteristic. Of finite type, finite topological type, meaning that the fundamental group is finitely generated, and then it is equipped with a, well, hyperbolic metric of finite area and say complete and finite area. So this gives me
But necessarily closed?
No, not necessarily. This is important point. Not necessarily closed. The fact that it is...
and you mean that the curvature is -1?
Yes, hyperbolic means constant curvature -1. Let us be a little bit more precise in this case. So we have the hyperbolic plane. This was discovered by our other hero here, Lobachevsky, right? Hyperbolic plane. We are used to think about it in models. You know, we have the disk model or the upper half plane model. In fact, everything can be done without models, and I like to work without models. And Lobachevsky tried to. I mean, he did everything, of course, without models. The models came more than 150 years after he. Not 150 years. More. Well, his first work on this was in 1825, and the models came 70 years after. So he worked everything. Everything I will say was known to him. In fact, without them. And anyway, so we have this hyperbolic plane. If you want, here we have the length element given by dx squared plus dy squared divided by y squared. This is important to, if you want to it's easier to do computations when you work with this. Here also here you have ds squared plus dy squared divided by the distance to the boundary square, or something that is maybe a factor 4, so that it is of constant curvature -1. There are a few important things which I will recall. Maybe once either here or at the seminar, I will give 1 or 2 talks just on hyperbolic geometry. But let's suppose now that you are familiar with this. So our surface may be closed or not, and being equipped with a hyperbolic metric means that we have these coordinate charts, you know, which arrive here in the hyperbolic space with change of coordinates are the restrictions of the hyperbolic space isometries, hyperbolic plane isometries. So this is the hyperbolic structure, and being complete and finite area, this is important. Let me recall what this means. Complete and finite area. Well, it means, you see here, so the surface may have some holes, missing points. So means that the neighborhood of each hole or of each missing point is a cusp. So a cusp is, you see, you have this model of the hyperplane. I mean, one way you have this I think it's Beltrami, this Beltrami embedding of a piece of a hyperbolic surface in Euclidean 3 space, and this This is a piece of a tractress. This is tractress rotating along the z-axis, and so this portion here is a cusp. Or otherwise, if you don't like this, a cusp is just if you use the upper half space model. You take two vertical lines from the form of the metric I gave you. These two vertical lines are geodesics, right? And from the form of the metric I gave you also, the Euclidean translations here are isometries, right? This is from the formula I gave you for the infinitesimal form of the metric. So there's a translation which gives me, which takes this vertical line to this vertical line, this geodesic to this geodesic, and this when I mod out the upper half plane by this translation, by this isometry, the quotient is a cylinder. The quotient is a cylinder, a hyperbolic cylinder, where one side of the cylinder is finite area, and this comes also from the formula I gave you of the metric. You see, and the other side is infinite area, and this is this one side of finite area is called a cusp. So this is very important for what will happen later. So a cusp, or otherwise a cusp, is a quotient of the region. Let's say y. This is x, and this is y. And then I take here a positive quotient of this region here, y greater than a, by some translation, by some Euclidean translation, which is also a hyperbolic translation, by a translation, a Euclidean translation, quotient of this region by some Euclidean translation, which we said is a hyperbolic isometry. So this is the setting. So we have these hyperbolic surfaces, and we want to measure distances between two surfaces, between two such surfaces, or between two hyperbolic structures on the same surface. So and get a metric on Teichmüller space. Yeah, let me say a word about metric. We will get a metric on Teichmüller space using this measure of distances, which I will tell you. This is called the Thurston metric, and this metric will satisfy all the axioms of metric spaces except the symmetry axiom. It is non-necessarily symmetric. The reason is that when I have two such hyperbolic metrics on the same surface, and then I consider the best Lipschitz map between them, then this best Lipschitz map, its inverse is not necessarily Lipschitz. in any way, and it's even less Lipschitz with the same constant. And the best Lipschitz map from one surface to the other, if I measure its Lipschitz constant, and I take the best Lipschitz map from the second surface to the first surface, I don't get the same number. This is why this metric is not symmetric. We'll see examples later. So maybe I recall also. I think I never wrote this definition correctly here. The definition of the Teichmüller space. So this is, we have a surface S. Now S is a topological surface. Topological surface of finite type and negative Euler characteristic. And then we want to consider the space of all hyperbolic structures on S. One first question, I don't want to go too much into the preliminaries, so the first question is, why is there a hyperbolic structure on S? Why is I take a surface and I told you what is a hyperbolic structures. We have these charts and so on. Why is there a hyperbolic structure on S? I'm not going to tell you now, but we shall see that there are many, in fact. We shall see that there are not only one, but a families of these. So S topological finite type surface, and then we consider the space of, so T of S is the set of hyperbolic structures on S. I just told you that this space is not empty. And then there's naturally an equivalence relation between hyperbolic structures, and I say that two hyperbolic metrics. You see, we talked about hyperbolic structures as given by a family of charts with coordinate change and so on, but it gives you also a metric on the surface because, well, the hyperbolic space is equipped with a metric. I gave you two formulas for the metric. You can think about them like this. So integrating this ds square, we can measure the length of paths, and we take the minimum distance between 2 points, we get the distance between them, so we have a metric. So hyperbolic structures are also metrics. Two hyperbolic metrics are equivalent if there exists an isometry between them which is, well, homotopic to identity. So for instance, you see this suppose this is a hyperbolic metric on S, on my surface S. That is, here I have a very short curve on the left. On the left-hand side, I have a very short curve, say like this. Where is this? And suppose I have well, this hyperbolic metric. So my intention was to draw the same, but with the now this is the handle which has a very small geodesic. So the same, but with a symmetry. there's a symmetry which takes me this metric to this metric, but these two metrics are not the same in Teichmüller space because the isometry which takes this metric to this metric is not homotopic to the identity. Okay, this is also important to note. Okay, so I didn't tell you now what is the definition of this Thurston metric. Now I want to tell you the definition. I'm starting with a different definition than the one I gave here a few days ago, so that I don't say the same things. Let me also mention here, I mean, something which is the basic, which belongs to the basics here, is that there is a topology. We will see there is a topology, in fact, there is a topology on, we called it T of S, which makes it homeomorphic to what? Homeomorphic to R, 6G minus 6 plus 2P, where G is the genus of the surface and P the number of punctures. There are several ways of seeing this topology. The topology will also come from the metric. I tell you how you define the topology with the metric that I'm talking about, even though it's not a symmetric metric, it induces somehow a topology. Let me mention that this result here is obviously for surfaces of finite type, since I have the genus and the number of punctures appearing here, they must be fine. There is a topology on Teichmüller space for surfaces of infinite type. The problem is that, I mean, one of the questions is that the topology is not, it has no natural topology, and the topology is not uniquely defined. You have several topologies, in fact. And one of the questions when people deal with Teichmüller spaces for surfaces of infinite type is to understand what is the right topology we are talking about. And a question is to compare various topologies on this space. And I'm talking about this because this Thurston metric on surfaces of infinite type, I don't know of any interesting result. I mean, I don't know what you can say about this metric or about the topologies inducing, about its geodesics, about its boundary, about anything. So the questions are open for. There are a lot of open questions for surfaces of infinite type. People who worked on surface of infinite type, essentially they use the quasi-conformal theory of Teichmüller space, which I'm not using today, or another theory, in fact, the theory of something with length spectrum, which is not the thing I'm talking about now, which is not. So you can. I know that you can. This definition, which I will tell you now about Lipschitz maps, you can make it work for surfaces of infinite type, but I mean, I can only give the definition. I don't know anything else. Okay, so this is. Let me now give the definition of this metric. So first, okay, so we have G and H, two hyperbolic metrics on S, and then we can take F from, well, SG to SH. And for x and y, x different from y in x, I can form this quotient, the distance between f of x, f of y, divided by the distance between x and y. And then I can define the Lipschitz constant of f as the, well, the supremum over all x different from y of this. This is natural definition of the Lipschitz constant of f. Okay? This is natural definition of the Lipschitz constant of f. And then I define the distance. This is the Thurston distance between, well, G and H as the log of the infimum over all f of Lipschitz constant of f over all f. What is f here? Oh, I'm taking the infimum over all. What do you suggest? Over all what?
Homeomorphisms.
Yeah, right. Over all homeomorphisms. Homotopic to the identity. Homotopic to the identity. Okay, thank you. To show, so we already said that there's no reason that d of gh is equal to d of hg, and we shall see examples later on. But the other properties of a metric should be satisfied, in fact, like the triangle inequality. This is easy. Can you see why this is satisfied? Yes? What did you say?
Yeah. Yes.
Yes, okay. Okay, so this is good. Triangle equality is good. The other thing is that L of GH is always positive and is 0 if and only if, well, G is equal to H. I'm from the beginning I'm mixing the things. I mean, G and H represent either hyperbolic structures or equivalence classes of hyperbolic structures. You see this distance here, since I'm taking the infimum over all homeomorphism homotopic to the identity, is not only a distance between hyperbolic structures, but it's also a distance. It's also a function on Teichmüller space because I mean the equivalence relation there to be homotopic hyperbolic structures goes. I mean it's taken care of in the fact that f is homeomorphism. I'm taking infimum over all f. Okay, so I can measure distances between hyperbolic structures, and I can measure distances between elements of Teichmüller space, and this is now.
L is D or what's L? L is D or what?
Ah, you are right. Thank you. I want to call it L. Yes, I call it D. I want to call it L like Lipschitz.
And the slope was non-negative.
L is yeah, the logarithm, yeah, L is non-negative. L is non-negative, so it means that this infimum here is always greater than 1. Greater than 1, and it's equal to 1 only if the two
because area is fixed, right?
Yeah, exactly, because the area is fixed. Yeah, there's a little argument here. In fact, it's a theorem in Thurston's preprint, and it has to do with the fact that the area is the same. The area is the same. The area, because if you have a map with Lipschitz constant strictly less than 1, then you can cover the surface by small disks, you know, small disks covering the whole area, and then if it's strictly less than 1, then one of the disks is sent to a strictly smaller disk, and the area is not present. And yeah, anyway, so this is one of the things, and that's it. So we have this metric. We have this metric, and I want to. So the basic technical tool, in fact, which will come several times. The basic technical tool is a Lipschitz map from one ideal triangle to another ideal triangle. Let me say a few words about this. Let me remind you first what is an ideal triangle. Ideal triangle. This is a triangle whose 3 vertices are at infinity, so it's a triangle in the hyperbolic plane. You can draw it like this. You can think of it in a model, but you're not obliged, in fact, because Lobachevsky knew knew a lot of things about ideal triangles. You know, he worked with ideal triangles. He worked also with ideal tetrahedra in 3 dimensions and so on. Without using any model. So this is just the existence of this. Of such a figure, the ideal triangle comes from the axioms of geometry. You know, this famous parallel axiom, which is not satisfied, and its converse is satisfied. So when you have a line, it tells you that when you have a line, you have at any point on the line, you have an asymptote here, and then you have an asymptote there, and then when this point goes to infinity, you find an ideal triangle. So you have ideal triangles. We just need to know that you have ideal triangles in hyperbolic geometry, and then something else which is very important in hyperbolic geometry is that you have these notions of horocycles. This was also well known to Lobachevsky without models, but if you want to talk about models, and these are geodesics which are all asymptotic, which are all converging to the same point at infinity, and then you have centered at this point at infinity, you have a family of curves intersecting these geodesics at right angles. So you can just, I'm just taking the perpendicular foliation, and this is a foliation by horocycles. We have other definitions as limits of circles. Limits of circles, you see limits. You see, you take up in the hyperbolic plane. Let's do it like this. You take a geodesic, and then you take a circle here, whose center is on this geodesic and passing through this point, and you make it greater and greater and greater, and the limit is a horocycle. The limit is a horocycle. In Euclidean geometry, the limit is just a line. It's a Euclidean line. You don't have horocycles. But in hyperbolic geometry, the limits of these circles are horocycles. So these are all horocycles here. So anyway, you have these. Something also which is important to recall is that in fact in hyperbolic geometry, there's up to hyperbolic isometry. There's only one ideal triangle. All ideal triangles are isometric. There are several ways to see this. In principle, I don't like to give the same argument as the usual argument. So my argument is this one. In hyperbolic geometry, like in spherical geometry, when you have a triangle, the three sides determine completely the triangle, unlike in Euclidean geometry. There are trigonometric formulas which give you the angles of a triangle in terms of the length of the sides, and these were also known to Lobachevsky. It's in all his books. And here you have a triangle, and if you have two ideal triangles, then the three sides are isometric. They are all infinite. Okay, so they determine completely the triangle. So the two ideal triangles are isometric. Okay, you can make it more precise by taking limits and things like that. But this is one of the basic properties of hyperbolic geometry. You know, I told you trigonometric formulas. It comes from a trigonometric formulas. And Lobachevsky was, you know, he said something because there was this question of I mean, he was worried about the question of the contradiction and non-contradiction of his geometry, and he said that, I have the trigonometric formulas. He derived all the trigonometric formulas of hyperbolic geometry. He derives them using the trigonometric formulas of Euclidean geometry and of spherical geometry. He has a way, in fact, very interesting way of deriving the trigonometric formulas of hyperbolic triangles. The Euclidean geometry comes from the fact, in fact, that he proved that the horospheres, which is a generalization of horocycles, the horospheres have a Euclidean structure. This he knew, and he proved. And he also proved the fact that when you have a triangle, then if you take so the proof is always three-dimensional. In his proof of the trigonometric formulas for plane triangles is always three-dimensional, and he is using also a sphere, a geometric sphere around each vertex, and he's using projection on this geometric sphere, and he is using the spherical geometry of this sphere because he proved that a sphere, a geometric sphere in hyperbolic free space, is in fact the usual sphere. It's the usual sphere that we have in spherical geometry, or the usual round sphere in Euclidean space. So he said, I found all these trigonometric formulas using spherical and Euclidean geometry, and if there were a contradiction, then there would be a contradiction in either in spherical or in Euclidean geometry. And then the other remark is that once he found the trigonometric formulas, then he knows all the geometry. In fact, he said all the geometry is contained in this trigonometric formula. So he was aware of all these things. So we have the he had the horosphere, he had the horocycles, he had the triangles, and so on. So the only thing now I will use is this ideal triangle, which is which we know now is unique, and in order to simplify and to use less imagination, we can draw it here in the Poincaré model, like everybody does. And this ideal triangle is equipped with this foliation by horocycles centered at the three vertices. These are the horocycles. There's only this is uniquely defined. This is uniquely defined, and then Thurston defines a Lipschitz map. Now we don't need this anymore. We just need the triangle. A Lipschitz map from the triangle to itself. By being the identity here on this region which is non-foliated, and then it sends each piece of horocycle at distance x. Let's put it here, to this piece of horocycle here at distance kx. And this is a K Lipschitz map. So it's sending a piece of horocycle at distance x to a distance to, let's take it greater or equal to 1, to a piece of horocycle at distance kx, and then it's sending it on the horocycle. I'm choosing all the most natural coordinates, the linear coordinates. Okay, I find coordinates here. Yes. Huh? Yeah, right. I'm starting with a k constant which is strictly greater than 1, but let's assume for k equals 1, then I'm not doing anything. This is a k Lipschitz map from the ideal triangle to itself. Of course, it's not a best Lipschitz map, because the best Lipschitz map from the ideal triangle to itself is just the identity map, right? So this is a more I'm complicating the matter here. The point is that this K Lipschitz map between from one triangle, from one ideal triangle to itself, he will combine it with other K Lipschitz maps from one ideal triangle to itself to construct K Lipschitz map from the surface to itself. So you can we shall do this. We shall do this more precisely later, but suppose that your surface is decomposed by pieces of geodesics like this into ideal triangles, right? each of these ideal triangles is equipped with its horocyclic foliation, right? So I get a kind of a foliation here on my surface. You notice that this horocyclic foliation, as we mentioned, is perpendicular to the boundary. I told you that these pieces of these horocycles centered at this point of infinity are the this is the perpendicular foliation to this family of geodesics going to this point at infinity. So these pieces of horocycles are all perpendicular to the boundary, and on the surface they fit well, and they give you at least a C1 foliation, because at least a differentiable foliation, because they coincide. They are when I mean on these breaks they have the same direction. They are perpendicular to the to these geodesic lines, and now I do a K-Lipschitz map on each of these triangles. Okay, on each of these triangles here, on each of these ideal triangles, I perform a K-Lipschitz map with the same K.
You do
Huh?
a K for each triangle. One and the same?
Yeah, for each, yeah, K is the same. K is the same for each of these triangles. I do a K-Lipschitz map, and I say that these K-Lipschitz maps, they fit together, and they give me a K-Lipschitz map on the hyperbolic surface.
I don't understand. If we have two adjacent ideal triangles, what about those middle points on the sides?
They are uniquely defined.
They are uniquely defined by the triangle. But
Yes.
But they.
Yes.
So do they always one and the same? So if we have two triangles that share an edge, it is one and the same point.
Yeah, this is a good question. We don't talk about this now. You're right. This is a good question. Yeah, it's not the same. 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 But I still have this map. It's not the same. I still have this map. This is a K-Lipschitz map.
Not the same. Then it's not continuous.
Yeah, we will talk about. Yeah, you're right. You're right. You are very good. Yeah, you're right. K-Lipschitz maps between, we will do something about that later on. Between hyperbolic surfaces, K-Lipschitz map between hyperbolic surfaces. Okay, this is.
Now it's
Yes.
interest only on each triangle, not because it's not continuous. It cannot be K-Lipschitz on.
Yes, you are right. There is this problem, but we will deal with this later. We will deal with this later, but we will deal with this later on the boundaries. K-Lipschitz map on the interior, if you want, of the triangles. And there are families. There are families of these. By making, so there's a family. So this is the kind of thing which we will talk about. There's a family by making K from 1 to infinity, and this family is called well, this is what is called a stretched line. This is called what is a stretched line, and it gives me a line in Teichmüller space. It gives me a line in Teichmüller space. We shall define it later on in a better way. You see, we shall define it later on in a better way. And this is a line which is a geodesic for Thurston's metric, provided we define it correctly. This is a geodesic for Thurston's metric. This is one result. I'm not proving this. We shall see this later. But this is So the first thing that we know about this metric is that it exists, and I can describe some geodesics for this metric. And the question is, yes?
One side geodesic, so it's not symmetry.
Yeah, it's not. Yes, you're right. Yes, it is one-sided geodesic. Yes, this is a very good point, because the inverse of this K-Lipschitz map is not a K-Lipschitz map. In fact, it's not Lipschitz at all. It's not the Lipschitz constant of the inverse of this map on this ideal triangle is infinity. This is because, well, this is because you see this is also something which Lobachevsky uses, but you can compute it easily using this metric ds square dx square plus dy square divided by y square. You compute the lengths of these pieces of horocycles. The length of these pieces of horocycles is exponentially decreasing, and the Lipschitz constant in the reverse direction is unbounded, because the contraction is more and more severe, and goes to zero. So the inverse for the inverse map, the contraction is infinite. Am I saying it clearly? Okay, so you are right here. This is a one-sided geodesic. One of the things I want to talk about, in fact, not today, but in this series of lectures, is are there two-sided geodesics? That is, geodesics where when you traverse them in one side, in one direction, they are geodesic, but if you traverse them in the other direction, they are also geodesics. And the answer is yes. The answer is yes. I will show you. So these will not be. There are geodesics in this space which are not stretched lines. There are other geodesics than stretched lines. This is one important thing to know. Before we stop for a break, let me tell you an easier setting. Well, in principle, an easier setting where all this theory can be developed, and this is the setting of ideal polygons. So I take an ideal polygon, say an ideal pentagon. I know that, well, you know that, so this is 1, 2, 3, 4, 5, and this is 1, 2, 3, 4, 5. You know that ideal polygons do not have necessarily the same shape. They are not all isometric. It's not like ideal triangles. And I can ask you what is, can you find, and from the geometry of the polygon, can you find the distance between them, the best Lipschitz constant, in terms of whatever you like, in fact, in terms of what is the best Lipschitz constant between two arbitrary polygons, provided I have a way of parameterizing the edges, and before studying the pentagons, you can study this tetragons, quadrilaterals. So if you want to follow Thurston's outline, the natural thing is to cut this into ideal triangles. Each ideal triangle is equipped with its foliation by horocycles. Let's say this is here and this is here, this is here and this is here. Canonical foliation by horocycles. Okay. Now this canonical foliation by horocycles gives me let's do 1 minute this case of quadrilaterals. It gives me a parameter here, which is a shift parameter, and here there's another shift parameter between these two distinguished points on the boundary. Okay, you have shift parameters. In the other case, I have more than one shift parameters. I have two, and then I have the possibility of changing my triangulation. So what I want to do now, you see, what I want to do now here, the one parameter family of hyperbolic structures, the one parameter family of ideal quadrilaterals, which is my stretch line here. More precisely, they are given by multiplying these shift parameters by k. So in order to do it correctly, you know, I have to introduce these shift parameters. This is one indication of the answer to your question. Okay. There it's much more complicated. What I can do here for the case of the quadrilaterals, by changing the shift parameters, I can go from any ideal quadrilateral to any ideal quadrilateral. You see? There's only one parameter, and this is the shift parameter. Here, in this case, if I multiply, so suppose I have...
I'm sorry.
Yes.
So what is the best way of mapping this to that? So I should look at the shift... I should compare
yes.
blue
yes.
lengths,
yes.
divide one by another.
Yes.
And this is...
Yes, this is k. This is K. In this very special case. Here it's much more complicated. Yes? Huh?
It could be negative.
No. Yeah. Well, you have to take absolute values. No. You're right. You're right. I mean, I'm simplifying.
Well, so there is an orientation on that blue thing.
No, you don't need orientations. In fact, you don't need orientations.
So there are two special
yes.
Then they might come in this order and on the other picture.
If it's 0, then you cannot do anything. You cannot move. This is correct. This is correct.
Okay, let it be non-zero.
Yes.
They can. So here they can look like this, and on the other
exact
like that.
Exact. So I can stretch from one side, and then from 0 I stay still if the shifts are 0, and then I can shift on the other side when the shift is yes. Here you can see you cannot do the same. I mean, first so here you see. Of course, you can define these stretch lines. You have these shifts here, and you have a shift here, and then you can define a stretch line by multiplying all the shifts by k, right?
Why can't we do the same with the pattern?
Because we cannot. Because if I do this, I cannot go. I cannot go. Okay.
It's like a tree.
Yeah, I cannot go from an arbitrary hyperbolic structure on the pentagon to another hyperbolic structure on the pentagon by doing just one straight line. This is what I'm saying.
Yes.
Yes. So you have to have a method from the beginning which tells you, okay, first of all, what triangulations do I choose? This one or the other one? Well, the other one, you don't have. You can't have one other one. You have many other ones. Which triangulations you choose, right? So you start with two. You start with two hyperbolic structures on the pentagons, and you want to triangulate them in a way such that, well, as you say, there's a tree. I cannot expect to do only one stretch line to go from one to the other. I have to move along one. Yes, exact. Piecewise geodesics. This is the idea. This is the idea which Thurston generalizes for the closer. Yes, but let me just say that this case of the ideal pentagons is not. I mean, I never saw this. I mean, nobody did it clearly. In fact, it's not. I mean, I think it's a good problem. The question is. Study the Teichmüller space of an ideal, n-gon, a theory which is parallel to that theory for closed surfaces, which is in Thurston's paper, and this is still not done.
Could you please?
This is a problem for you, Gayan. Yes? Yes?
I wanted to ask, could you please formulate explicitly what is about quadrilaterals?
Okay, quadrilaterals. Okay, quadrilaterals. If I there's a center here for this space of quadrilaterals. This space of quadrilaterals has a center. It has a distinguished point, a point where these a point where these shifts are the shift here is 0. So I cannot do anything here. I cannot multiply the shift by, I mean, if I'm, but if it's non-zero, then I can move from one structure to the other. And the statement is that this is a geodesic for Thurston's metric.
And if you triangulate it in the other way, then you get...
No, I think that if it's the center, it says the center. Yeah, right. Yes.
Both ways, but no,
yes.
But if there is a geodesic.
Yes. Right. Yes. 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 You have another one. Yes. You have another one. You have another one. This anyway, I didn't say, but this space is definitely not. This metric is not uniquely geodesic. You have, in general, you may have different geodesics from between one point and another. Mm-hmm. Okay. Mm-hmm. Yes. So maybe we stop for a little while.
I think yes, it's time.
And then we start again with for more. How much later?
5 minutes.
5 minutes, yeah. And then we do what, half an hour or? Okay, so I will explain now again. I want to explain a few things, and then I left here because I will say a little bit more about this. I want to give it. I want to say it more precisely. What are these stretched lines? For this, we need. I need to talk about measured foliations. Do you remember what is this? Okay, so it's good, so I can talk about it. So I kept it here before I want to finish with the definitions of the Thurston metric. So I want to give another definition here. Another definition of the Thurston metric. So this has to do with the length spectrum of the two surfaces. So L of GH can also be computed by comparing the length spectra of G and H. More precisely, let us give a name to this set. So S, script S, this is the set of, well, let's take it simple. Simple closed geodesics. On S, not geodesics. Let's start with. It's better to start with simple closed essential curves. Essential meaning that they have a geodesic in their homotopy class. For instance, this curve is not essential because it can be made smaller and smaller and smaller and smaller. Not only this, but there's no geodesic in its homotopy class. Okay, and this curve also is not essential because there's no geodesic in its homotopy class. You see, in hyperbolic geometry, if the curvature were not constant, if the curvature could be positive or whatever, then such a curve may have a geodesic in its homotopy class. I mean, if you take the definition of the geodesic Riemannian definition on the sphere, you have these great circles which are geodesics, and they all bound disk. I mean, they are homotopic to 0, but they bound disk. But in hyperbolic geometry, if a curve does not bound a disk or is not homotopic to a cusp, then there is a unique geodesic in its homotopy class whose length is the smallest length of the curves in this homotopy class. Anyway, so this is simple closed essential curves.
Homotopy class from them.
Do you need what?
S is the set of homotopy.
Yes, you are right. You are right. Thank you. Homotopy classes of simple closed essential curves, and this when I take hyperbolic structure, then this becomes in one-to-one correspondence with the set of simple closed geodesics. Okay, this is good. And then for alpha in S, there's this quantity which and for alpha in S and G and H in Teichmüller space or hyperbolic structures or equivalence classes of hyperbolic structures, then I define this, well, let's say G H of alpha as the length of alpha with respect to H divided by the length of alpha with respect to G. This is a quantity. Okay. And then, well, I define, now we use K of GH given two hyperbolic structures or elements in Teichmüller space, G and H. This is, well, let's say the log of the supremum of RGH of alpha, the supremum for alpha in S. Okay, I take the supremum of all these ratios over all simple closed curves, and then I get a quantity which I denote by K, and the result here, this is a theorem. I wrote it somewhere. I wrote it somewhere here. No, I didn't write it, in fact, but this is a theorem in section 10 something, and in fact I wanted to, this is not, I mean, this is one of the elaborate, this is one of the difficult theorems. The theorem says that K is equal to L. This is one of Thurston's theorem. He proves that the two definitions of a metric coincide, and okay, so you can work either with one metric, or you can work with the other metric, or you can work with both. Let me say right now that if you take the case of surfaces with boundary, then the metric L, then L is different from K anyway for surfaces with boundary. The metric L is not adapted to surfaces with boundary because it can be positive, it can be negative, it can be negative. No, which one? Sorry, the metric K. The metric K can be negative. That is, if you have a surface with boundary, you can equip it with two hyperbolic structures D and H such that this supremum here is strictly less than 1. So the logarithm becomes negative. So this is not good for surfaces with boundary, whereas the metric L gives you a reasonable metric for surfaces with boundary. There is a modification of K for surfaces with boundary, which I will talk about later, not today. The metric L does not need to be modified. The modification of the metric K for surfaces with boundary gives you a very nice theory, in fact, which we will talk about. The metric L, I'm not sure. I don't know. I don't know. I think nobody tried to develop this theory of L for surfaces with boundary. So this is one thing. The fact that K equals 0 if and only if G equals H for G equals H has elements in Teichmüller space. This is not a trivial element. In fact, this is something which Thurston shows in his paper. He has a two-line proof of this. You can think about this if you want. Okay, so now I want to come back to this thing, and I want to say it a little bit more precisely, because I want to explain something. Maybe I will explain it. I will explain this theorem next time. But today I want to start a little bit by some preliminaries. You see, to define these stretch lines correctly, I want to use this language of measured foliations. So, okay, you remember that a measured foliation a measured foliation is a foliation on the surface S equipped with an invariant measure on transversals. So this foliation by horocycles, if I take a transversal like this, then I declare, in fact, that the transverse measure of this transversal is the length of its projection on either side of the triangle. Okay, and because the horocyclic foliation is perpendicular and so on, I mean there's a symmetry from here to here. This transverse measure is the same whether you project on this side and this side. Okay. Now we come back to this picture where implicitly, you see, I have something like a decomposition of my surface with these bi-infinite geodesics, which the cells are all ideal triangles. It's called an ideal triangulation of my hyperbolic surface. Okay, this ideal triangulation of my hyperbolic surface induces a measured foliation on the surface. And now we can be more precise. The transverse measure, in fact, that when I glue, what I'm saying is that when I glue two ideal triangles to get my surface, this is one and this is another one here. Then the transverse measure, which is this hyperbolic length, coincide, and so I have a well-defined transverse measure for transversal, which in the transversals which intersect more than one ideal triangle. Okay. So lambda now is an ideal triangulation of my surface S. S is equipped with a hyperbolic metric G. This is lambda. Lambda is the union of these by infinite geodesics. I mean, you have to show that this exists, but let's suppose that the existence of these ideal triangulations is of the same kind of reasoning than the existence of geodesics in homotopy classes of simple closed curves. Okay, it's exactly the same kind of reason, exactly the same kind of reasoning. So when you decompose your surface into okay, when you take on the surface a curve, a simple closed curve, which is not homotopic to a point or to a cusp, there is a unique geodesic in this homotopy class. Okay, this we already know. When you take a topological arc from the cusp to the cusp, a topological arc which is also non-trivial, which I cannot. This is a trivial arc. I mean, I don't want an arc like this. Then there is a unique geodesic line in this in the homotopy class of this arc with endpoints fixed. For exactly the same reason as the existence of the closed geodesic, and if I take a family of simple closed curves which are all non-homotopic and essential and non-intersecting, then the geodesics I get are also disjoint and non-homotopic and so on. Okay, we can do this later. I mean, I can give you a course on hyperbolic geometry, but this thing we need to know. And for exactly the same reason, if you take a collection of arcs joined cusp to cusp, which are essential and non-pairwise homotopic and and disjoint, then you have a unique geodesic in each representative of each arc, and the union of these arcs is disjoint. And you take a maximal collection of such arcs, you get a decomposition of the surface by ideal triangles. If you get something more complicated than ideal triangles, then it means that you can add one more arc like this, which we said is not possible because we took a maximal one. So anyway, you have ideal triangle of SG, and the ideal triangulation gives you a well-defined measured foliation. A well-defined measured foliation on the surface, which is obtained by gluing all these foliations by horocycles. Okay? There's a result now, which is one of the theorems which is proven in this paper of Thurston. Given now an ideal triangulation, you see, which a topological ideal triangulation I don't have the hyperbolic structure. Given the topological ideal triangulation, and given a transverse measured foliation to it, transverse to this ideal triangulation, there is a unique hyperbolic structure such that this ideal triangulation is a geodesic triangulation, and the transverse foliation is the foliation by horocycles. Let me write it in this way. There is a bijection, in fact, more than a bijection. It is a homeomorphism. There's a homeomorphism between what and what. So this homeomorphism, I said, this is given an ideal triangulation, given a topological ideal triangulation of S. There's a homeomorphism between Teichmüller space and space of measured foliations transverse to lambda. This is lambda. I'm parametrizing the hyperbolic structures with measured foliations. And this homeomorphism is such that it is such that when lambda is made geodesic, so when I take a point here, then I can make lambda geodesic for this hyperbolic metric, then the associated measured foliation here, the associated one, is the horocyclic foliation. This is all this is up to equivalence, but you understand, okay? And this is a difficult theorem. In fact, this is one of the, maybe the proof is, I don't know, I don't remember exactly, but maybe 15 or 20 pages in this. This is kind of this is really a uniformization theorem, you know. Thurston is proving a uniformization theorem, and it's not only for ideal triangulations. It's more generally, in fact. I think you saw this with the seminar, Gayani's seminar. This is more generally, lambda is a geodesic lamination, in fact. Geodesic lamination with complementary components, which are triangles. This is important now. Because to have this geodesic lamination with complementary components are triangles, I can do this on closed surfaces. I don't need any more to have I don't need anymore to have this cusp to have the triangulation. I have these ideal triangles covering my surface, topological ideal triangles covering my surface, and the statement is, for every choice of a hyperbolic structure, I can make this topological ideal triangulation, which is in fact a geodesic lamination. I can make it geodesic. And then I have I can define in each ideal triangle. I can define my measured foliation. These measured foliations in ideal triangles fit well together. They are perpendicular to the lamination, and then they give you a geodesic lamination, a measured foliation on the surface. And this correspondence is 1-to-1. This correspondence is 1-to-1. And again, in this construction, I mean, there is this construction in the inverse construction. There is this construction of a hyperbolic metric on the surface, and this is what I said is a uniformization theorem. Okay. So now, if we come back to this thing here, to the stretch line. Okay. Now here in Teichmüller space, if you want to make it more precise, what I said here, the stretch lines are the families of measured foliations obtained by multiplying the transverse measure by a constant. This is the stretch line. This is the definition of the stretch line now. A stretch line is defined via this passage here to measured foliations, and in this parametrization there's an R plus action. There's an action by the positive reals on the space of measured foliation, just multiplying the transverse measure by a constant. So I can multiply it by a positive. I have to multiply by a constant greater than 1, and then this family of measured foliations here. Well, k between 1 and infinity. This family here gives me a family of hyperbolic metrics, which are called the stretch lines, and which are geodesic for Thurston's metric. Okay, and the first theorem I will prove to you about this. This is the first theorem I proved in this context. This is I told you I started 30 years ago, and the last theorem is 2019, just this year, in fact. And this is the first theorem, which I want to. I will talk about. I will talk about the things which I know how to prove. This is why I'm talking about this theorem which I proved. Let's keep this. This. So you have this Teichmüller space, which we represent as a ball, and then you know that you have several boundaries. One of them is Thurston's boundary. One of these boundaries is Thurston's boundary, which I will recall to you next time. And the first result I want to prove is a limiting result. It says that a stretch line a stretch line has a well-defined, has a limit, well-defined endpoint, has a well-defined endpoint on Thurston's boundary. I will describe to you this endpoint. I will tell you what is this endpoint, and I will, in this occasion, next time, I will explain a little bit what is Thurston's boundary, so that you know what is Thurston's boundary before I prove this. And then one question which more or less you raised there is, what about what about the other direction? Well, in reverse direction, these stretch lines in the reverse direction, which are not necessarily geodesics, but they exist, in fact. They exist. They are lines in Teichmüller space. Well, in some cases, they have a well-defined, they have a limit. They have a limit on Thurston's boundary, even in the cases, I mean, even if they are not geodesics in this other direction, in some cases they don't have. In some cases they don't have, and I will also explain this. So maybe this is yes.
I have a stupid question.
Yes.
Don't we arrive in the reverse direction to the most symmetric case when all these shifts are zero?
This is very good. This is a very good question. This is a very good question. But now,
Not always.
No, you are right, because you are thinking about this. I didn't talk about this case of the yes. Yes, you are talking about this case. You are thinking about this case. In fact, I forgot to talk about it. This is correct. This is correct. But this is something else here. This is something else because the shifts. I mean, the shifts. You see, in the general case, we were not going to talk about shifts anymore. I talk about the shift just because I wanted something discrete. You know, I'm talking about something discrete here, and here. But we'll take another point of view. Yes, this case with shift, I think it's very interesting. You know, I think it's very interesting. But I think nobody had time, or nobody had the idea to understand it. It's a kind of a discrete analog. It's a kind of a discrete analog of, I mean, discrete because you have the lamination here. The lamination which appears here is not a discrete lamination. It's something which is much more complicated. Here it's and you have a finite number of triangles, you see, and a finite number of parameters, finite number these shift parameters which you know, and yeah. Okay, so I will stop here now. Yes, yeah, please.
In the positive direction.
Yes.
So indeed you have a point which is an unmeasured lamination.
Yeah, a point which is a measured lamination.
Because I'm just trying to imagine what happens when you go along this geodesic line.
In fact, you will.
I think in terms of these shifts. So each time you know where to turn. When you cross an edge of an ideal triangle, you go along your.
Yes, here in fact, in my case, the positive limit point will be this will be exactly this measured lamination here. It will be exactly this geodesic measured lamination.
Unmeasured.
No, it is measured.
It is measured.
Yeah, it is measured. It is measured. The one which is unmeasured is, I mean, the measured foliation, which is the horocyclic foliation. Right? The unmeasured foliation is this one here. It's the one with it, which we started with the triangle. This is the unmeasured foliation. And this is sometimes, I mean, if it happens to be measured foliation, this triangulation, you know, this unmeasured foliation, then it will be a limit in the reverse direction.
That's complicated for me. Okay. Okay.
The same questions appear in the classical Teichmüller theory. In fact, where instead of limits of stretched lines, people study limits of Teichmüller geodesics. You know, with respect to first and boundary, there have been many results on this over the years. In fact, the results on this started maybe 40 years ago, and the last results, I mean the most complete results, it's maybe 3 or 5 years ago, something like that. So this is also, I mean, all these questions about limits of geodesics were addressed in the classical quasi-conformal Teichmüller theory.
And could you also please comment on the following? So you say that if we fix the triangulation, the ideal triangulation, then the Teichmüller space is homeomorphic to the measured foliations, but not all of them, but those that are transverse.
Yes.
But
yes.
At the same time, measured foliations, if we projectivize them, they give us the boundary of the Teichmüller space.
Yes.
So, and is there interplay between looking at some of
yes.
places as the elements of the Teichmüller space, and on the other side, on the other hand, they sit on the boundary?
Yeah, this is precisely this theorem. Because on these measured foliations which are transverse to the lamination, you have this R action, this positive real action. This is it, and then you go to the boundary. Yes. So you are getting some charts near the boundary. So this parametrization of Teichmüller space extends to a parametrization of the compactified Teichmüller space with the equipped with the Thurston boundary. This is, yes, you are right. This is one good way to see this. Yes, you are getting charts near the boundary.
Can you draw a measure of foliation which is not transverse to lamination?
Sometimes you see this lamination, which we talked about, this lambda, it could be itself a measured foliation. You see?
But so, okay, what does it mean to be not transverse?
But itself is not transverse to itself. This is an example.
I see.
So you must exclude this. For this parametrization here excludes this foliation, this measured lamination. If it is measured, it excludes all of the measured laminations which are topologically which are topologically equivalent to it. But it excludes also. You see, if you have two measured laminations. We are talking here about laminations and foliations. So suppose you have measured lamination, which has several components in general, and one which suppose lambda 1 is one of these components. If you take a measured foliation f now, which has 0 intersection number with one component, then you cannot realize it as a transverse foliation. Because if you realize it transversely, then you can read the intersection number. And playing with this, you know, you get all the cases. Those who are made transverse are those those who can be made transverse are those who have non-zero intersection number with each component. you can make a precise statement here. It is transverse to the lamination if and only if it has non-zero. I mean, it has a representative which is transverse to the lamination if and only if it has non-zero intersection number with each component of the lamination. If the lamination is measured laminations, that is, if intersection number makes sense. Otherwise, the lamination which we started with, for example, like this one, maybe not a measured lamination, so this is something else now.